The general procedure for hypothesis tests when we're concerned with qualitative data is typically captured through what is known as a chi-squared test. And so the chi-squared test operates by thinking about the frequency distribution or the contingency table of the underlying data that we have observed, and then hypothesizing something about the world, which in turn gives rise to an expected frequency distribution or contingency table. The observed data is then compared to the expected data, and by operating in this way, we're actually able to derive a test statistic that will have a chi-squared distribution, hence giving rise to a chi-squared hypothesis test. Regardless of the hypothesis that's being tested, if we are comparing the expected to the observed contingency table or the expected to the observed frequency distribution, this is going to give rise to a chi-squared test statistic. And so they become very versatile tests when we're dealing with qualitative data that have been summarized through their frequency distribution. So when we're given a hypothesis that's been translated into an expected observation, the chi-squared test can be performed. So what is the actual logic of the test? What are we actually thinking about doing in this case? Well, suppose that we have data that are collected and they're represented as either a contingency table or a frequency distribution. So our data are either going to be qualitative to begin, which give naturally rise to a frequency distribution or a contingency table, or if they're numeric, they're either discrete, again with the natural translation to a frequency distribution or a contingency table, or they've been discretized, so they've been converted into discrete data. We're going to denote the observations as either OI, if we're talking about a frequency distribution, where recall that a frequency distribution is going to have the number of observations for each of our categories, so we'll have O1, O2, O3 for as many categories as we have. Or if we're in a contingency table, then we need to use two different indices, and so then we'll use OIJ. And so O11 is going to be the first cell in our contingency table, and then O12 is going to give us our second cell, and so forth. Now, suppose that we have a null model of some sort that's going to be used to generate expected counts for the corresponding distribution. So the null model is going to come from some observation or some hypothesis about the world, be that a concrete distribution or the assumption of independence or something else, and that is going to give rise to a probability distribution. That probability distribution is going to be able to be used to calculate the expected counts for the number of observations we would expect to see in our frequency distribution or contingency table. So we can take those expectations and we'll denote those as either EI, again if we are talking about frequency distributions, or EIJ if we're talking about contingency tables. And so then, notably here, E1 is going to be the expected value that corresponds to O1 as our observed value, or E12 is going to correspond to O12, right? So there's exactly the same number, there's exactly the same structure. When we have O's, those are corresponding to observations. When we have E's, those are corresponding to expected values. Now, if the null model is correct, then what we should expect is that OI and EI are going to be close to each other. Right? If the assumption that you're making about the data that generates those expected values is actually correct, then we should observe something that is close to the expected value, at least on average. We can, of course, say the same thing if we're talking about our contingency table. So OIJ should be close to EIJ. And if that's not the case, if those data points are not actually close to each other, so if OI and EI are far apart, then that's going to be providing evidence against the hypothesis that was used to generate the expected counts. Right? If we are always finding that the expected count is far from the observed count, then that suggests that whatever is generating those expected counts probably is not correct. And so we are in this situation where the closeness or the farness of our observations with our expectations somehow gives rise to an assessment of the likelihood of our hypothesis. Okay? So by combining the observed and the expected counts, this is going to produce a test statistic that has a chi-squared null distribution, which again is why we refer to this as the chi-squared test. So what is the formal test statistic here? Well, formally, the test statistic of interest is going to be this that we call the chi-squared test statistic here. Okay, and so what we do is we sum over all of our possible categories. So I equals 1 to k, we're thinking about a frequency distribution here. We're going to have inside of the summation, we take OI minus EI, so the observed minus the expected. We square that value, and then we divide by the expected value here. And so we're going to do this for each of the values within our the frequency distribution. And this is going to give rise to what we call the chi-squared test statistic here. In order to compute this, we only need to know the observed values, which are the actual data that we have, and the expected value, which is going to be coming out of the null model. And again, within each term here, if the null hypothesis is actually correct, we should expect that OI is close to EI, and so then this whole term in the numerator here should be small, right? And so then that would make the whole test statistic small, and that sort of would suggest that the null hypothesis might be correct. On the other hand, if those are large differences, then we're expecting that the null hypothesis is probably not correct. Okay. If we have a contingency table, then we have the exact same statistic here. We just have to make sure that we're summing over both the rows and the columns here. So we take every observed value minus every expected value squared over every expected value. And we sum up all of the possible values across the whole table. Right? And so there's really no difference between using the frequency distribution or the contingency table. We just need to make sure we're summing up all of the possible differences. Now, if the expected values, again, are close to our observed values, then the value of this chi-squared test statistic is going to be small. So if the null model fits, we would expect chi-squared to be around 0, right? If it was a perfect fit, then it would be exactly equal to 0 because OI would equal EI for all of the different values. In practice, we would expect this to be a small value. Now, on the other hand, if it's a large value, then the null model is probably a poor fit. So in this sense, what we can say is that this is always going to be a one-tailed hypothesis test, right? So if we think about, well, what values are actually going to be contradicting our null hypothesis, the only values that are going to contradict the null hypothesis is if we have OI being far from EI. And because we end up squaring this, right, this is always going to be a positive large value if they're far from each other, right? And so then that makes chi-squared into a large positive value. And on the whole, this is always going to become a large positive value. And so in this sense, the one-tailed p-value is always going to be our p-value from our chi-squared test statistic. So in order to actually work out, well, what is that p-value? Where is that coming from? We need to know the null distribution. And so in order to find the null distribution of the chi-squared statistic, the name is sort of suggestive as to the distribution we're going to be turning to here, right? So generally, chi-squared is going to follow a chi-squared distribution, right? That's why we give it the name there, right? We call the chi-squared statistic the chi-squared. It follows a chi-squared distribution. Chi-squared distributions are characterized by the number of degrees of freedom that they have, and so in order for us to work out specifically what null distribution are we working with, we need to know how many degrees of freedom are there for this chi-squared distribution. And so the general rule is that it's going to be equal to the number of data points that are free to vary based on the null model that we're making. Right, so the degrees of freedom is going to relate to how did we actually have to calculate those expected values. When we were calculating the expected values, how many values were actually constrained within our data. Okay, so when calculating our expected quantities, how many items must remain fixed here. So in our example, where we have a candy manufacturer, which is filling packages with 25 candies, 5 different colors, right? So we have our red, blue, green, yellow, and orange. Okay, so when we're thinking through this example here, we know that there's going to be an expected value of 5 per color, right? So there's going to be 5 for red, 5 for blue, 5 for green, 5 for yellow, 5 for orange, giving us our 25 total. And we can calculate this out directly based on that assumption there. However, we also know that the total sum of all of our expected values has to be 25. Right? And so we have these 5 numbers. We know that ultimately they're all going to have an expected value of 5, but we also know that their sum has to be 25. And so once we calculate that it's going to be 5 for red, 5 for blue, 5 for green, and 5 for yellow, right, if we're going in order here, well then we have allocated a total of 20 candies already, right? And there's still one category left. However, we know that the sum has to be 25. And so we don't actually get to calculate the total number for orange, right? In this case, the total number for orange is constrained because we know that the sum has to be 25. Right? And so even if it had been sort of different numbers for each of those categories, that last value is always going to be constrained because we need to sum to 25. So in other words, if you want to take 5 numbers and you know that they have to sum up to 25, you can pick the first 4 to be whatever you want them to be. But as soon as you've picked the first 4, that fifth number is determined because the sum has to be 25. And so in this case, there's not going to be 5 numbers that we're calculating. We're really only calculating 4, and the fifth one is going to be implied on the basis of the constraints that we have. So we don't calculate the total for orange. It must be 5 since we're constrained to have a sum of 25, and therefore we have four degrees of freedom. There are actually 4 things that are free to vary. We're actually calculating 4 different quantities here. Okay. So while the degrees of freedom can sort of always be worked out, again, in this way, it's going to be common for us to use 3 different hypotheses, either assuming some specific distribution, assuming homogeneity between 2 different populations, or 2 or more populations rather, or assuming independence between 2 quantities. And so for each of these assumptions, we can concretely work out, well, how many degrees of freedom are there going to be? And so if we suppose a concrete distribution, then there is going to be a total of k minus 1 degrees of freedom, where k is going to be the number of categories that we have. And we saw that in that previous example. As soon as you've calculated those k minus 1, that last category is going to be constrained by the overall total, right? So that's what we saw previously. Because we need the overall total to be the same, that means you can only actually calculate k minus 1 values. The last value has to be whatever it's sort of left over with. If we're going to make the assumption of homogeneity, and we have k populations, the assumption is that they're homogeneous on a trait with L levels, right? So we're thinking about sort of a k by L contingency table here. Then there's going to be a total of k minus 1 times L minus 1 degrees of freedom. Okay? And this is going to come out because we actually have sort of 2 sets of constraints here. The population totals and the category totals are going to be constrained, right? We have to sum the rows to the same things, and we have to sum the columns to the same things. And so in this case, if you work out, well, how many values does that leave free? It's going to turn out that that leaves k minus 1 times L minus 1 values free. And so you could work through that process yourself, counting up the constraints there, or you can remember that there are k minus 1 times L minus 1 degrees of freedom here. It's much the same process as in the previous example. The difference is that here, because you have 2 different sets of totals that have to be remained, we sort of have the same thing going on within each row and within each column. Okay. Now with independence, right, we're thinking about there being 2 traits here. One of them has k levels, the other one has L levels, and we're assuming that those 2 traits are independent. It's going to turn out there are exactly the same number of degrees of freedom as with our homogeneity example, right? So there's going to be k minus 1 times L minus 1 degrees of freedom. We're looking at a contingency table that has effectively the same structure, and we're imposing effectively the same constraint on it. And so there ends up being the same number of degrees of freedom in that case, right? So we have our category totals being fixed for both our rows and our columns. So once we know our null distribution, we know how many degrees of freedom there are, then we have to calculate our p-value. Okay, and so suppose that we've calculated that the chi-squared test statistic is equal to x for some particular sample. Then the p-value is going to be calculated based on this chi-squared nu distribution, where the nu is the number of degrees of freedom that we've worked out based on the hypothesis here. So if we take fv to be the cumulative distribution function, or f nu rather, to be the cumulative distribution function for our chi-squared distribution, then the p-value is going to be the probability that the chi-squared test statistic, right, which follows, again, this chi-squared nu distribution, is greater than what we've observed, which is 1 minus the probability CDF here. Right? And so our p-value is going to be a 1 tail, and it's specifically going to be the upper tail in our chi-squared test. Right? And this will always hold no matter what hypothesis we're thinking about here. If we're using statistical software, we're thinking about R, then this can be computed as 1 minus p chi-squared, and then we plug in our test statistic and the number of degrees of freedom here. Right? And so p chi-squared is going to correspond to our CDF here. Now, for specific distributions, right, the number of degrees of freedom is going to be k minus 1, and so we get that there. If we're instead looking at homogeneity, the number of degrees of freedom is going to be k minus 1 times L minus 1, and so we're looking at that specific version there. And then for independence, we're looking at k minus 1 times L minus 1 as well, right? And so we get those specific calls for the specific assumptions here. Now, again, it's worth emphasizing, a chi-squared test is always only going to be looking at a 1 tail p-value. We are never going to consider the lower tail on our chi-squared test. And that's because if we think about it, small values for our chi-squared test statistic, values that are close to 0, are actually going to be in support of the null hypothesis, right? And so we do not view that as evidence against the null hypothesis. So in addition to the actual process here, we have to think about, well, what are the assumptions? What are the requirements for this test to be valid? The null distribution is actually the result of an approximation, and it's going to rely on 3 separate assumptions. The first is that we actually need to be assuming that we're doing simple random sampling from a single population, or in the case of homogeneity, for multiple populations, okay? And so we need to be actually going out into the population and drawing a simple random sample from that population. If we're not taking a simple random sample, then the chi-squared test statistic is not actually going to be justified in this way, okay? And so the first thing is going to be about the way that sampling has occurred. The second, and this is going to be the most common assumption to actually check, is that the expected value for every cell has to be sufficiently large. There's going to be different standards for what we call to be sufficiently large, but once you've worked out, well, what are the expected values, none of those values can be small. As a general rule of thumb, all of the counts should be at least 5, but depending on the source that you're looking at, some individuals might say that the count should be 10, some individuals might say that the count should be at least 5 for, say, 80% of the observations. The general rule is sort of, if you're seeing a lot of small values, 0s, 1s, 2s, that kind of thing, then the chi-squared test is not going to be appropriate in that setting. And so you want to make sure that the chi-squared expected values are actually quite large. One thing to note is that this also puts an implicit constraint on the overall sample size to be sufficiently large, right? Because if you have a small overall sample size and you have enough categories, then you're always going to end up with small expected values, right? So if you think about a total of, say, 100 individuals, but you're spreading those 100 individuals over, say, 25 categories, then there's going to be some categories that have, 4 or fewer observations within them, or expected observations in them. Okay, and so if you have even a largish sample, it has to be large relative to the number of categories that you're thinking about. Okay. The last assumption, it's a common assumption to make for most of our statistical inferential procedures, is that all of the observations have to be independent of one another, right? So we're thinking about them as having sort of no correlation, no dependence between them. Again, that is not to say that the traits have to be independent, right? That's a test we can actually run, but it is to say that the different individuals that we've sampled should be independent of one another. Oftentimes, this independence will come from our random sampling, but we still should be careful about that. And so with all of that, that sort of gives rise to the overarching chi-squared test. So the chi-squared test is going to proceed by computing a test statistic that compares our observed values to the expected counts, and that's ultimately going to give rise to a chi-squared distribution. We can work out how many degrees of freedom this distribution needs, either through the concrete assumptions that we're often looking at, or instead by doing the direct calculation. The p-value is going to be the upper tail p-value for that hypothesis. Calculating that p-value out of the chi-squared is going to be leading to valid conclusions, or approximately valid conclusions, as long as we have those assumptions met, the assumptions of random sampling, of large expected values, and of independence within the sample. And so under these settings, or in this setting, the chi-squared procedure becomes a very versatile procedure for testing statistics or testing hypotheses regarding qualitative data. It's most frequently applied for those 3 hypotheses that we've seen, but it is going to apply in sort of a broad range of scenarios, and it's a very useful tool to add to your statistical inference toolbox.